minutes. I thought the Indian time is 9 o'clock, right?
Yes, sir. It's 5 to 9 right now.
Oh, yeah, 5 to 9. Oh, gosh. I got it completely mixed. Okay, no problem. So I just shared, and how many papers have you had?
Sir, submission is 620.
620.
620, and we accept 144.
Oh, okay, good.
And quality is good because actually, see, out of 620, we have a 200 recommendation from tax chair, but
Right.
technical chair is Nisat, Dr. Nisat, and Dr. Saad has selected 144 only.
Okay. I got the timing wrong. I thought I got another half an hour. Do a lot of people dial in to join the video presentations, virtual, or they don't?
Who's that?
Do a lot of people join in the video presentation or virtual?
Yes. Virtual only. Actually, we asking them to submit video presentation and join the session for the question answer round only.
Yes, I understand. For you had the conference yesterday too. Did a lot of people join in?
Yes, sir.
How many join in? 100? 50?
No, actually, fast keynote session 170.
Yeah, okay. Then drop down, I think.
Then drop down, and because parallel session is going on now, was going on. So every session split the number, no?
Okay. Understand.
And sir, this session will be live in YouTube live stream also.
Or is it?
Yes.
I think, I don't know whether I got some other things that you should not put it on live YouTube, because the reason is some sensitive material here. I didn't know that. Can you not put it on I will tell you whether to put it on.
No, actually, sir, if you want, we can run as live and then remove from YouTube.
Okay.
Okay, so greetings to you all, ladies and gentlemen. Today we've got a great keynote speaker for you, and it's actually quite an honor for me to introduce him. He's going to talk about V2X technologies, and his name is Professor Udaya K. Madawala. Professor Udaya K. Madawala graduated with a Bachelor of Science Electrical Engineering Honours degree from the University of Moratuwa, Sri Lanka in 1987 and received his PhD Power Electronics from the University of Auckland, New Zealand in 1993 as a Commonwealth doctoral scholar. At the completion of his PhD, he was employed by Fish and Paykel Limited, New Zealand, as a research and development engineer to develop new technologies for motor drives. In 1997, he joined the Department of Electrical and Computer Engineering at the University of Auckland, and at present, as a full professor, he focuses on a number of power electronics projects related to bidirectional wireless EV charging systems for V2X applications. Professor Udaya is a fellow of the IEEE and a distinguished lecturer of the IEEE Power Electronics Society, and he has over 30 years of both industry and research experience in the fields of power electronics and energy. He has served both the IEEE Power Electronics and Industrial Electronics Societies in numerous roles relating to editorial, advisory, conference, technical committees, and chapter activities. Currently, Professor Udaya is an associate editor for IEEE Transactions on Power Electronics and a member of both the Administrative Committee and Membership Development Committee of the IEEE Power Electronics Society. He was the General Chair of the second IEEE Southern Power Electronics Conference 2016, held in New Zealand, and is also Chair of SPEC Steering Committee. Udaya, who has over 300 journals and conference publications, holds a number of patents related to wireless power transfer and power converters, and is a consultant to industry. Ladies and gentlemen, help me welcome Professor Udaya to the platform.
Thank you very much for this kind introduction. First of all, I would like to thank the organizing committee for giving me an opportunity to talk about what I've been doing for the last 10 years in relation to bidirectional wireless power transfer. My topic today is about V2X technologies, and the V stand for vehicles, and vehicle to X technologies, and X can be anything, and whether we are going to go wired or wireless. So that's what I'm going to talk about. Electric vehicles. So when we think about electric vehicles, and we can say that, and they can be regarded as the means of future transport, and mainly because they reduce pollution, enable efficient and clean transport. They're ideal for sustainable living. And not only that, and we can use the battery electric vehicle as an alternative energy storage to offer services such as grid services. For an example, and put this in context, and if you look at the world electricity supply by storage technologies, and you can see that it's coming from pump hydro to EV storage to utility scale battery systems. From 2020 to, if you look at 2050, the time span there, and the EV storage is taking and take up of EV storage much higher. So as you can see that, so the EV batteries are expected to be the largest means of energy storage worldwide. Even by 2030, you can see, and it's going to be quite significant proportion of the storage is taken by the EV batteries. So that means that the installation of bidirectional, because when we have the batteries, we had to have bidirectional capability. So the installation of bidirectional chargers in commercial and workplace settings will become the standard. Just to have a look at the global EV sales by country. I'll just get rid of my right. By country, look at the sales by country. From 2015, if we take China, 207,400 electric vehicles. In 2018, 1.256, and that is about million there. And 2019, I haven't got the latest figures, but you can see that from 2015 to 2018, within a span of 4 years, it's been increased by 5-fold. And if you take the global total EV sales from 500,000 to about 2.2 million, that's again more than the 4 times what was in 2015. Now this is EV sales and by country. And if you take the EV sales by EV type at global level, and of course in China, the BYD and bike there, in 2017 it is 114,000, and in 2009 it has gone to 219,000, actually it is to be updated. But nevertheless, if you look at in 2018, it's almost double, 215,000. And if you take bike there, 96,000 to 160,000, again double there. And if you take Tesla, and can you imagine that it is from 93,000 to 360,000 there. And it's a rapid escalation of the uptake of electric vehicles. So what we can say is this trend is going to continue. And if this is going to continue, and there are some challenges. The first one is the charging rate, and that of course the power level. That depends on many issues, many aspects, an electric vehicle, the type of the electric vehicle, the grid, the weak or strong, and the charging systems, and the standards, etc. And of course, now the latest chargers they offer, and that you can go and charge in less than 30 minutes. So some very high power chargers are available too. Actually, what happens to the battery is a different concern. And when we do fast charging, but these are some of the challenges. And the other one is the distance to charge, and that's called the range anxiety. But then again, people are working on different technologies, and many advances are taking place. And then again, the distance per charge, that depends on the electric vehicle and what the capacity is, the battery. So the new vehicles are coming into the market, the Chevrolet Bolt and the Kia and the Hyundai and the Tesla models, and they actually offer nearly 250 to 370 miles on a single charge. So the range is increasing and the technology is developing, and we can expect that this is going to continue too. And more than that, even the range is going to be extended with one charging. And there are more and more charging stations that's going to be installed too. So that's what the future is going to be. And then we had to comply with the standard, and it's available. I will talk a little bit later on this. The other issue is the battery, the size and the weight and the cost and the life and the disposal, and these are concerns. And if you take lithium-ion batteries, these are the ones that we use. They have very high energy density from 100 to 265 watt-hours per kilogram, but still significantly heavy and bulky and expensive. And for an example, and if we take the weight of a Nissan Leaf, that is 24 kilowatt hour, and that's about 200 kilograms, whereas the Tesla Model S in 85 kilowatt hours capacity, and that is 540 kilograms. That's quite heavy. And the cost, approximately about 130 to 145 kilowatt per hour. That was in 2016. This is one of the most expensive items. But it's going to, and GM is targeting by 2021, it's going to come down to $100 per kilowatt hour. And this is this area too, and the technology is improving and the prices are expected to come down. And lifespan, that's again a concern too, generally 3 to 8 years, or about 100 kilometers. And more technologies coming into the market. And for an example, again, a Chinese car battery manufacturer says that it is ready to manufacture a product capable of powering a vehicle for 1.2 million, and that's about 2 million kilometers across the course of a 16-year time. So that's what the future is going to be. Not only that, in Brazil, in the university, in the UK, developing a better voltaic batteries made from man-made diamonds, and they can offer and constant current lasting for thousands of years. So that's what the future is going to be. And that's about the battery, the vehicle itself, and the power level. Then what about the impact on the grid? And it's very easy to say that the EV uptake is very high, and there are many incentives. And what would be the impact on the grid? And that's another concern. And just imagine that whether it is everyone is going to work and coming home and charging. It could be single, it could be hundred millions of vehicles. If, for an example, if you take China, I think they are going to go fully electric in 2040. And what will happen? Everyone coming home and start charging. What would be the impact on the grid? And so this, of course, the increased power demand in the UK alone, and 700,000 EVs expected in 2020 this year. So that is extra 500 megawatts of power. Where does it come from? And not only coming from, and can the existing power network can facilitate, can cater for that power demand? So what it means is there may be some upgrades to the power network, substation infrastructure, and that would be unavoidable. It's essential there. So these are the challenges associated with having more and more electric vehicles and being used. And some of these challenges, especially the impact on the grid and with existing infrastructure, and can be managed or addressed through optimized smart charging strategies. And for example, I'm just going to give, though it is not the main focus of my talk, I'm going to talk a little bit about what I did for very recently for in Indonesia. So they want to have a look at that. What would be the impact on the distribution network in Jakarta, Indonesia, depending on the uptake of the electric vehicle, whether they have to upgrade their system, even the distribution level, transformers, whether the network can cope up with this EV uptake in future, and that is to combat the pollution in Jakarta. And if it is so, and how can we mitigate that problem, and what would be the extent the EV penetration that should be allowed? So we look into that one. We came up with an idea. We had a case study in a particular area. We look at some of the transformers and their capacities. And based on that, we came up with a new idea. How can we mitigate the problem with the distribution operator? And this is what we came up with. And this is, I'll just show you this. We came up with smart charging based approach based on the transformer loading, and I wouldn't go into too much details on this one here. And there it is. So we looked only at the distribution transformer loading, and based on that, and we tried to optimize the charging so that, and the charging can be taken place, or we can force the charging to take place within the capabilities of the transformer. And now if you look at it on the left-hand side, obviously there are different scenarios, scenario 1 and 2 and 3 and 4, and the 4 is the more penetration. There you can see at night that it's going to, under these conditions, there are more penetration, and it's going to exceed the transformer limit. So what can we do? We came up with this particular way of doing that, and with the controller by looking at the transformer loading, and we can distribute the charging pattern there. And so that we can somehow or other mitigate this issue. There you can see on the right-hand side, in the blue curve there, we can actually bring down well below, still the same number of vehicles can be charged in a manner that is the energy shifting then. And that is within the capabilities of the transformer. So many people have done similar approaches there. So what I'm trying to explain is that, and this is another way of mitigating the problems that are associated with the impact on the distribution network, or as well as the power network. And it's the same transformer. Look at the voltage problem, what actually happens, not the transformer loading. And if it is end of the line there, if it's a weak line, what would happen to the line? Can we cater for our customers or consumers that connect to that line? And there you can see that the voltage drop under scenario 4 is 4 into 0.82. And that exceeds the allowable limit in Indonesia. So what can we do? How we can mitigate the problem? So with our method, and you can see that we have managed to prop up again to increase the voltage from 0.882 to 0.925 per unit there. So what it means is without any upgrade, without any augmentation, still we can somehow or other mitigate that issue. And because of the EV, more EV penetration. So that's about the impact on the grid. So if you leave that aside, so this is about the electric vehicles. What are the challenges? Then of course we had to charge electric vehicles. So the question is if we are going to go wired or wireless. And if you go wired, and that is more or less established, it's relatively simple. You just connect the wires or the cable there, and let the infrastructure change. Standard is established there. It's the EJ1772 in use at present. Now wireless is going to be the the future. And the car comes and parks, wirelessly gets charged. And it's robust, safe, and convenient. Ice, water, doesn't matter, and you can just charge. But huge infrastructure change in comparison to wired charging there, as opposed to just connecting a cable. The standards being developed, in my opinion, cannot be deployed everywhere. And just imagine that in third world countries, and where the infrastructure and so the minimal, the level there, how can we have such a advanced technology? It may not be easy, perhaps in the urban areas. And this is at the development stage. And then I'm going to talk a little bit more about the wireless during the course of my talk. And if you got the wired charging standard or AC or DC there, of course, then you must be very familiar with that now. This is more and more available on the net. And there you can see the different level, AC level 1, AC level 2, and that's the low power level. Then you go to DC level 1 and 2. And there you can see on board and off board. The main reason is the off board is the charging power level is very high. It cannot be on board, and because of it, it's quite heavy. And that's a commercial entity. And there you can see the input and the power level there. And that ranges from 50,000 volts, 400 amps. And then you have the, that is the American standard SAE, and then you have the IEC, the European, and same as very similar to the Chinese standard too. And then we have the protocols that you can see, the combo one, the combined charging system, CCS, and the US, and the German one, and the CHAdeMO that is coming from Japan, and of course the Chinese one, GBT, and the supercharger Tesla. And these are the different types of connections, and you may be familiar with that. And here you have on the top, and that's the European one. The bottom is the one that you have, the American one there. On the right, the CHAdeMO, and that is the combo charger, the DC fast charger connector there. It's not the combo, sorry, fast charging connection there. And here's the charging system, level 1, level 2. As you can see that the level 2, it comes with that. You can see the charge itself is located outside the vehicle, cannot be mounted, and it's obvious. And this is a much higher, I think 25 kilowatts CHAdeMO old charger, and this is the Tesla charger there. Now, that is about a little bit about wired. I didn't go too much details into wired. And let's have a look at the wireless EV charging. So the wireless EV charging, that is basically based on inductive power transfer. That is because basically based on inductive coupling. So what actually happens is here we have a charger, here's a coil, it's buried. And there you can see on the left-hand side, and you have the grid on the right-hand side there. So the car comes and parks on top of the coil, which you call the charging pad there. And underneath the car, and there's another coil, and that is mounted, and the ground pad. And we excite with the high frequency, and it creates a magnetic field. And this magnetic field links with the coil that is mounted underneath the vehicle, and through the magnetic coupling, power transfer takes place. And that is actually inductively coupled power transfer wirelessly. It's taking place through the magnetic medium. There you can see the arrow is only one direction. At the moment, the power is being taken from the grid and being stored energy in the battery there. So you can see this is the unidirectional charge. So therefore, about 10 years ago, I wanted to start working on the bidirectional. In other words, I can use the car battery, or may not be only the car, anything. The wirelessly, I can transfer power in the both direction there. So that's called the bidirectional wireless power transfer. So, and here is a typical wireless EV charging system. There you can see on the left-hand side, on the bottom there, and you have the electric, the grid there, 50 hertz, it's low frequency. Then we have a converter. From low frequency, we convert into high frequency. Then we have a compensation circuit, which I will explain a little bit later. And after the compensation circuit, then we excite the primary coupler that creates a magnetic field at high frequency, which is again coupled to another the coil mounted underneath the vehicle there, and through that magnetic coupling, and the power transfer takes place. So the power is transferred from the ground side to the vehicle side, and on the vehicle we have a compensation circuit, and we can call the secondary or pickup, and also the power converter, and that actually stores energy or power the vehicle there. So the one on the ground side we call the ground assembly, and one on the car we call the vehicle assembly. So even with like other charging, and EVs, and the wireless charging has some challenges. And the one is whether it's going to be stationary or both stationary and dynamic. The dynamic is the one that's going to be future, perhaps I will not cover today in my talk. And that is when the car is traveling at 100 kilometers per hour, dynamically getting charged and wirelessly. So then we had to generate this power and the pulses of energy coming, whether it is tertiary, if it is dynamic, and that has to be generated and absorbed by the battery. Then we had to provide electronics to wirelessly transfer that energy. So these are the challenges there. So what is the power level? How we're going to generate it efficient way? And the power, the flow can be either uni or bidirectional. So that depends on the system. And also this takes place, the wireless power, at a higher frequency, which I will again mention soon. It's at 85 kilohertz, not at 50 hertz. So power conversion, and these are all wireless power transfer systems are high-load resonance circuit, mainly because the coupling is very poor. As opposed to a transformer there, as you know that, as it's wireless, so the power transfer takes place across an air gap, and air gap could be quite large. And so given that the air gap is quite large, the coupling is very small, and a lot of war requirements there. So in order to minimize the war requirement, and we use resonance circuit there, and the resonance circuit can be assessed, that's a series, parallel, depending on, and each of these circuits will have different characteristics. And that is how we compensate. And then we can have the controller. It can be active or passive. And then, of course, one other important aspect that is not what I've been working on, the magnetic pad or the coupler design. So magnetic pads, and that's where the magnetic field is created, the coil design. And can you think about the different cars may have and different coils, a coil design. And we can see that in the one car goes and going to charge at a charging station, if we may have a different pad design, the coil design there. So we had to have interoperability. And how do we design the magnetic couplers, the pads, more efficient and the least amount of material, and the leakage is minimal, but you had a maximum coupling. So a lot of work has been gone into that, to research, and people have proposed and implemented successfully. They range from circular, so DD, DDQ, and bipole, etc. These are different types of pads, and they have different characteristics and different performance there. And also one of the important aspects is the alignment, and which I will come back a little bit later, and how do we align. And then, of course, we had the communication, especially this is important for the V2X system, which I will talk soon to, and that is from transferring power from both ways, and we had to have communication. Not only that, with the charging protocols involved, and communication too, and the compliance and with standards. And these are related to the safety, EMF, F4D, foreign object detection, and live object detection. And people, they should be very safe. And also, what are the emissions? And there are some standards in relation to that too. And of course, the physical construction, cost, and the robustness, etc. And the standard for wireless EV charging that's being implemented, and that's called J2954 and LDEV. LD stands for light duty, and J2954/2, that's for heavy duty vehicles there. And this is going to be released, I think, early this year. I'm not sure what happened. I think it's going to come out very soon too. And they look into the safety, performance, interoperability, communication, control, foreign object detection, and the living object detection, etc. All these issues. And they've been more or less ready. I think it's been tested now. And the nominal frequency now agreed to at 85 kilohertz. In other words, the charging takes place at 85 kilohertz, but we had the window of variations there. Not all the time there. You can look into that frequency. That is from 79 to 90 kilohertz. And the minimum efficiency target when the coils are aligned, and that's about 85%. And it's not aligned, that's about 80% offset there. And these are the classes. And for light duty electric vehicle, there you can see that it changes from 3.7 to 22 kVA. And the charging pads or the charging coils or the couplers, and of course that depends on the power class and the interoperability and the shapes. different coil designs, as I explained before, and the ground assembly, and that can be ground surface flush mounted or below the ground surface there, and the distance across which, or the air gap across which the charging takes place, that changes. That's called the Z class, and that changes from 100 to 250 millimeters. And if you want to know a little bit more about that, and you can Google and you can find out some of the standards which is available. So now, my talk is about V2X concept. So the X stands for anything. And the V is vehicle to anything, X. So the question is, electric vehicles, are they going to be used only for commuting? And not, of course. And as we know that this is not new, V2G and G2V concept, that what we can do is off peak time, we can charge, and the peak time we can put the energy back into the grid, or in fact, you can use it. That's V2G, G2V concept, or else we can have the building to a home to vehicle, or the building to vehicle, or home to vehicle, or the other way around too, and the vehicle to buildings or vehicle to home there. And so that is again you're using the vehicle battery as the energy storage. And then we had the vehicle to vehicle. And I talked about that a long time ago, and then the people in fact laughed at me when I talked about that. And now you must be still thinking that it's possible or not. And one example is like this. And let's say it's just charging a fleet of electric vehicles. And there you can have the limited capability of the grid supply. And there are some cars coming. And let's assume that, and these red arrows represent the thickness of that, the charging level, the power level, let's say that. So the last car came that in a hurry to get charged, but it more power from the charging, in a short period of time. So, but if the total power level exceeds the capability of the system, what can they do is the other cars can put the energy back. And you can see from the bottom side, two bottom electric vehicles, the arrows being changed, they are putting energy back into the system. For an example, there can be a rebate for them. They are not in a hurry. So they can put the energy back, and the other car can be charged quickly. And exactly the same way, another car comes, now still the demand cannot be met in a hurry, and the last car on the bottom, and then it can give the energy back in there. So this is called the V2V. This is one of the scenarios, the charging fleet of vehicles. So what is important for all these applications, if you look at, is this. V2X compatible electric vehicles. So you have the grid side or whatever the X, you can say the building, home or whatever. On the right side, you have the electric vehicle. So what we need is the bidirectional charge. So it can be wired or wireless. So I'm going to talk about the wireless charging and the technology that we developed. So here's the bidirectional wireless power transfer the system. And it's a typical system there. There you can see on the left-hand side, the grid, AC grid, and the right-hand side, the output, of course, the electric vehicle battery there. There you can see the low frequency converter. It's called the low frequency converter. It is from 50 hertz to DC. And we have the DC link there. From the DC link, we convert that into high frequency. We have a high frequency converter. And that is because the power transfer takes place at 85 kilohertz. And here's charging coils, and here, and there, of course, the air gap across which the charging, the power transfer takes place. And the M is the mutual coupling, which is quite between the two coils. And as I mentioned before, it is quite the coupling is quite low. And this side is called the ground assembly, and that side is the vehicle assembly. And if I take this compensation, as you can see that we have compensation, which I mentioned briefly earlier. So if you look at, before we go into that, why we need compensation and what sort of compensation networks being employed, let's take this part here. So I only took the DC part, and I haven't, we can talk a little bit later what the grid interface is going to be. If I take this part here, this is what it looks like. This is a type of a compensation there. This is called the LCL or parallel tune. So what actually means is that when we select the capacitor, inductors and the capacitors, in such a manner they connect in parallel, LCL, in a manner that, and we're looking from the input side, like unity power factor, they can sort of resonate at the frequency of operation. So frequency of operation or frequency of power transfer is 85 kilohertz. At 85 kilohertz, it appears like this is a resistive load here. So there's no VAR requirement. So why we need one requirement? If you take a transformer, the coupling is extremely very high and very close to 1, whereas for this coupling it's going to be 0.3 to 0.4. So what it means is to have a given amount of power transfer to the battery, you had to source a lot of VARs, increase in the VA rating of the converter. So that is not actually quite efficient way of doing that. So that is why we use these resonant converters, so that we can minimize the VA rating for a given amount of power transfer. So this is essential for all wireless power transfer system. So this is what I'm showing here is called LCL, parallel tune. You can have series tune or series compensated. So some call it tuned, some call it compensated, the same meaning. Okay, so this one is LCL, parallel tune. So if I now under tune condition, if I look at the power transfer, and this is what I can write, and there you can see the power transfer going from either way, from left to the right, to the right to the left, in other words, grid to the vehicle or the vehicle to the grid. And there you can see, and there are 3 variables for a given battery voltage or the input voltage there. So of course, in this situation here, this is the 8th order system in this particular case, and this is under resonant condition is the one that we can write this equation. That doesn't happen all the time. Okay, so how do we control? We can't do PWM. This takes place at 85 kilohertz power transfer. What we do the phase shift modulation there. So the 5P and 5S are the ones that we use to modulate. So you can control the voltages of the 2 converters normally, and then the angle and between the voltages produced by the 2 converters, we keep it at constant value at 90 degrees. So at the plus or minus 90 or plus 90 or minus 90, and that will dictate whether the power flow is from the grid to the vehicle or vehicle to the grid there. And if you want to control the amount of power, and we simply control 5P or 5S with the phase shift modulation there. And not only that, and we had to have some sort of a synchronization on the secondary side, because everything taking place wirelessly, so we had to lock into system. We had come up with numerous ideas how to do it without a direct link or any communication. So just to show you, this is the first system that we built a long time ago, and there you can see there's a gap there and the power transfer takes place. And this is just quickly show the video there, and the power goes back and forth. So that we started doing about almost a decade ago, and since then we have come a long way and developed new technologies. Now here's the screenshot of some experimental system there. There you can see grid to vehicle. So you can see that if the grid side is, in this particular case, is leading the grid voltage, and the vehicle side, the inverter there you can see the power transfer takes place from grid to the electric vehicle, or the power flow. So here you can see from the arrow on the top there, that grid side converter is leading, whereas the vehicle side converter is lagging in comparison with respect to the grid side voltage here. So therefore the EV receives power. And here's another situation there. Now the V to G, and there you can see the EV supplies 3 kilowatt to the grid. So here you can see the electric vehicle that is leading in the grid side voltage there. So the power flow is reverse. It is V to G, earlier it is G to V. And here's another scenario there. You can see that one EV receives power, because if you look at the EV1 and the voltage waveform lagging the voltage wave from the grid side, and then if you look at the one in the EV2, and that is idling, because this is no in phase there, so no power transfer takes place. And here you can see the both electric vehicles, and they're leading, and therefore they are putting energy back into the grid there. So that's the technology that we developed quite a while ago. Now, there are some challenges. Okay, this is all good. And what I talked earlier was when all the pads are aligned. So what happens if they're misaligned? And how does it happen? And when the car comes and parks, invariably, okay, you can't 100% align the 2 pads. And they're prone both to lateral and longitudinal misalignment there. They go this way or that way there. So actually lateral and the longitudinal mainly that happens with dynamic charging, but nevertheless you can see that what I mean by the longitudinal and the lateral. And here just the representation, this illustration of what is happening. And there you can see on the left-hand side is the ground assembly there, and the vehicle comes and parks there. Depending on where it parks, there you can see it is subjected to this misalignment there. So that's when this happens, when it is misaligned, of course the coupling changes. Why the magnetic reluctance changes? So the magnetic reluctance changes, and consequence, and the coupling changes, the M changes. The M changes, even I can't write the equation there because it could be and changes in both the L1 and L2, or the primary side inductor and the secondary side inductance value there. But of course, that the change may be small depending on the extent to which the magnetic reluctance change, depending on the pad design too. But nevertheless, the power transfer will be affected. So what can you do? Of course, you can then have, and when this happens, I can write this equation as I said that. And what you can do, these inductances, the changes there, I can have a large pad, but that is not cost effective. Okay, so the one way to get around that problem is we have all these variables there. Perhaps we can look into and to change these variables, or using this variable to somehow or other compensate for the changing in the mutual inductance or the coupling, so that we can still mitigate the problem associated with the paired misalignment. In other words, still we can regulate power under any coupling change there. There are two ways of doing it. One way is to do in the passive way. Passive way is like this. So as I explained before, and we can use different type of compensation. Each compensation has different characteristics there. And some may be negative, some may be positive. But if we can combine two different types of compensations, and we can negate the bad effect of one compensation from the other compensation there. So in other words, and they are complementary. And here you can see that is a type of a system there on the top side, and you can see it is parallel tune, and on the bottom side is series tune, but they're connected together. So when you combine them together, the variation of mutual inductance of the coupling increases in one case, and the impact of that may be reduction in power. But if you look at the other compensation, and the impact would be reduction in power, but if you combine them together, you have more or less the constant power. Just to show how it works, and I'll show you this video. This is some of our group students prepared this one. And there you can see the movement in the pads there, and you can see this is quite low power at this stage. Okay, and to go to high power, I'll move it to a little bit high power level. There it is. You can see it's about 3 kilowatts, and you can see this is the hybrid system. So you can see 3 kilowatts, still power is constant, despite the large misalignment between the pads. So that is one way of doing that. The other way of doing that is, can we use a control mechanism to mitigate the problem associated with the misalignment there? So this is what we can do. So there are multiple variables. This can be done with bidirectional system. It's more like, actually it is impedance matching, and there you can see that there are 4 variables. Primary voltage, you can control with the duty cycle there, that's a phase shift. And the secondary voltage, of course, the frequency, and then of course the angle between these two voltages produced by the converters. Either you can have a full bridge converter, you can have a half bridge like this with the 2 switches there too. And so how do you do that? So now you have 4 variables there to control. Now how do you know that which value is the optimum value? So in other words, how do we determine the optimum value for the alpha, beta, and the phase angle and the frequency? And that will give the maximum efficiency, and also it will regulate the power despite any changes in the mutual inductance or the coupling there. So Power is always regulated, efficiency is maximum despite any pad misalignment or detuning. So we came up with a method, and this is two-stage optimization process, and we used 4 control variables. So what we do, the first stage, we optimize the AC to AC conversion stage. So in order to do that, we look into the AC here, and there we look into the load and the impedance there, and we are trying to look at what is the optimum impedance, load impedance for a given power level there, at which the efficiency is maximum. So once we know that one there you can see, find the optimum value, and from the maximum efficiency there, and we can find out, we can show that theoretically that what should the duty cycle, what should be the voltage produced by the second side converter. And that is related to the frequency and of course the mutual inductance. We don't have to know the mutual inductance, we can estimate it, and the change in coupling. And from that we know the voltage. They are knowing the voltage. Now what we do is we go to the second stage, and what we do is we optimize the DC to DC conversion. I know to do that, knowing the duty cycle on the secondary side, now I'll work out what should be the angle, of the phase cycle between the voltage and the currents, and that is seen by the secondary side there. In other words, the load. Okay, and then I can find out, that is to work out what is the minimum value that is required to have the zero voltage switching. That is to maximize the efficiency again. So once we know that one there, then what we do is we change the frequency to make sure that the reactance on this complete reactance on the secondary side, no VAS, is 0. So we keep on changing the frequency. And then what we do, we change the alpha, that is what should be the voltage that should be produced, and that depends on the power level for a given mutual coupling there. Okay, so that is what we did. And here is a control concept there. You can see on the right hand side, and you measure the power there, you control the voltage and the phase angle there. We have synchronized to the primary side there, and by looking in the input impedance of the primary side, and we can work out what should be the power requirement and the variation of the coupling, and from that we can work out what should the frequency of operation, and that frequency of operation the second side will lock in, and also what should the duty cycle of the primary side converter. So this is what we did with this is the optimal control. Now I'll show you some of the results for 1 kilowatt system. There you can see on the x-axis you can see the variation of the coupling, and there it changes from mutual inductance from 22 and the 60 there, and there you can see that there are 3 methods there. So normally the commonly used method, the 2 control variables, there's a dual phase shift and the triple phase shift, and our one with the 4 variable, all 4 variable, quite complex way to doing that one there. But all these methods that you can see in comparison to the one that we propose, that with the 4 variable optimal control with the minimum current. Whatever the conditions on this particular case, I think we are delivering about 1 kilowatt. And there you can see, irrespective of what the coupling is, the minimum is the current of the both sides are minimum. That means the maximum efficiency, same amount of power. And if you look at the system efficiency at various M and P output, there you can see that in the on the left-hand side is the maximum coupling, and the right-hand side, and is the M21 is the minimum coupling there. There you can see in the all scenarios, and from the power is varied from 200 to 1 kilowatt there, then the optimal control with the 4 variable give the highest efficiency there. Of course, on the right-hand side, that as you can see there, I think this is a series compensator circuit there. There you can see that the mutual inductance is quite small. As a result, to give the same amount of power, you have to have more currents. So consequently, the efficiency is slightly less in comparison to other cases, but nevertheless, in comparison to all other 2 methods, the efficiency is the highest with optimum control with 4 variables there. Now that's about the misalignment, and we talked about the wireless power transfer part. Now let's have a look at the grid interface, and that is this part here. Okay, so what we look at is DC-DC part, and that is all high frequency. And now we are going to look at from low frequency to high frequency part. So can we combine, this is a 2-stage process. Can we combine this low frequency converter and high frequency converter together and achieve the same thing? Of course, this matrix converter is not new, but then again, taking place at 85 kilohertz. It's not easy. I mean, 50 hertz people have done it, or 60 hertz, but 85 kilohertz in the both direction. It's not that easy. and we had a complex commutation algorithm there too. And now, of course, on top of that, there's a resonance circuit there. So, and here's what is happening, and direct 50 to 60 hertz, and then we can convert it to 85 kilohertz. I think at that time when we did this work, it's about 25 kilohertz, and it does not require large field inductor, reduce a link capacitor, reduce number of conversion stages, complex control strategy as I explained before. Now, if I simplify this, and what we have is a grid. So what we want to do is we have to transfer power and across the air gap, and with this one converter. So what only we can control is the grid current and the direction there. And that is the grid current and the direction there, because the grid voltage we assume to be constant. So if I get depending on the operation of the converter, if I get an expression for the grid current, you can see how complex it is. And that, of course, depends on the voltages produced by the two converters, and also the voltage, the angle between the two voltages there. So we normally keep the angle theta between the two voltages, and to control the direction of the power flow, and we control the phase shift to the voltages to control the amount of power. So how do we do that? When we look at that one there, this is what the grid current is going to be, and the same equation which I showed. But if you look at that, if we do it, if we lock into 151 or 52 theta for a given phi and theta, if you have phi 2, the square wave modulation there, you get, you can see the amount of harmonics, the generator. THD is very high, 48%, but it doesn't, it's not going to comply with the standard there. So we want to come up with an idea. So we came up with an idea how we can mitigate this issue. This is what I did. So what my students actually did. And there you can see that here's the dominant component of the grid plan. So we fixed the modulation, the phi 1 and the phi 2 and phi 1 and theta. Therefore, what we can do is we change phi 2. So for a given phi 1 and theta, what we do is we modulate the phi 2 linearly. So by modulating the phi 2 linearly in every cycle, we can have very nice and sinusoidal signal there for any given drop power. So the power is fixed by phi 1, right? And then we modulate phi 2 linearly. And there you can see on the results, there you can see that on the top one, and that is the maximum power grid power. There you can see the similar theoretical and the experimental results there. They are in phase. So you can see that the grid is actually giving power to the electric vehicle. And here the second scenario, and there of course you can see the green one is inverted now, so it's out of phase. What it means is now the vehicle is giving power back into the grid there. That is with the matrix converter. And here are the harmonics, THD, and you can see it's acceptable levels. And of course, the power factor is almost unity, and the efficiency is quite high. We have never actually optimized the efficiency there. And this is one of our recent the projects. And what we did is called the versatile wireless vehicle to grid home interface. So in other words, V2X system there. You can do a lot of things in this interface there. Just to see, and here's a scenario here. And here we have the grid there. It's connected to vehicle to grid home units there. Number of units. Now, if I take one unit here, and there you can see the wireless interface. And the wireless interface and the power can be transferred either direction, or the energy can be stored or retrieved wirelessly. And that is what I talked earlier. Now, this is connected to the house there, or the home there. This is non-linear household load there. So it has the load PL and QL, the reactive power, as well as the harmonic power. So normally what actually happens is that, and we can use this one and the vehicle to power interface to give the harmonic power what is required, QL and the reactive power and the harmonic power, and the grid should only provide the reactive power, nothing coming, no reactive power. So if I look at this one again, and this particular case that we can operate in 5 different modes, and there you can see APF, active power filter, and there you can see the grid is giving active power, what is required by the household, and of course the power interface will give only the reactive and the harmonic power. And then we had the grid is giving actually active power to the household as well as charging the vehicle, and the vehicle actually giving the reactive power and the harmonic power requirement of the household there. The next one is the vehicle is actually giving everything now. And the excess power what we have, the vehicle there, and that can put into the grid there, and also it meets the whole power requirement household. And the other one is the vehicle to grid to the home there. There you can see again, and the grid is giving active power, and the vehicle is giving some active power too. And that one is the islanded mode there. And I'll show some of the results before going to that. And this is how it works. And this is not only that, we did something extra and to improve the efficiency there. And here's a system, and this is what we described before, nothing new. So what it means is by controlling these two converters, I can control the power for wirelessly. Now here's a load, and it has the reactive power, active power, and the harmonic power. And this is the typical what the grid tie converter, and it only gives the active power there. So what actually happens is the grid has to give the whatever the active power requirement, meet the active power requirement, and the active power requirement depending on the load and also with the electric vehicle, whether it is giving power into the grid or taking power from the grid there. And on top of that, it has to meet all the reactive power requirement, the load. And what we do is we remove that one. Now the reactive power requirement, harmonic as well as the load reactive are now made by the power quality converter. And not only that, we modulate the DC link. Normally we keep the DC link voltage constant, but we came up with an idea that now we modulate the DC voltage depending on the power requirement, and so that we can optimize the operation of the wireless converter. Why? That we can minimize the switching losses by operating under zero voltage switching conditions there. So we, depending on the power requirement, we modulate the DC bus voltage there too. So I normally have some graphical representation of what actually happened. Given the time frame, I will just show you some results there. Okay, and here's one more. There you can see that, and that is the vehicle and the grid is giving power to the house there. So there you can see that the load power is 7.5 amps there, the THD is 48%, and the load power 430 watts in this particular case, and we just have a small prototype. And the PV gives minus 250 watts, and the grid supplements the 180 watts, so the 430 watts there. And there, of course, you can see the load VAS is 200 VAS, and the reactive power, whereas nothing being drawn from the grid, and you can see the grid voltage and the grid current unity power factor there. And then we go to the next mode there, and there, of course, again, it's the islanded mode. Everything is taken care of by the electric vehicle. There you can see the electric vehicle is now giving the power back into the household, and that is met, and the grid power is 0. And there you can see as a result, that is the amount of current that is injected into the interface, out from the interface, the house is increased because of the higher demand. And this is good to the house or the home there. And there you can see there's no vehicle at all. And there you can see that the grid voltage and grid current, and they are in phase there. And there, of course, the power interface. Okay, and the power interface taking care of all the harmonics there. And there you can see that one there. So it's a reactive power filter. And the next one is the grid is giving power to both to the house and the vehicle there. There you can see that the grid power has increased. You can see from the current there, increased current there. And there, of course, and that's what happens, 620 watts giving and 370 watts coming to the car there. And the other one is vehicle to a home and the grid. And as you can see, it's very self-explanatory what is actually happening. And I wouldn't go into too much detail given my time is running out. And here's the prototype that we built. Now the question is V2X. It is, or will this be a reality? And this is Nissan Leaf to Home. You must have heard that was released quite a while ago, about 2014 or 12. And that can supply, but that cannot be grid connected. And that can only power a house, and that will provide 2 days of household electricity. And that is from Nissan as CHAdeMO. And that is the new 3-phase system there with ENL and working on. And the V2X, it's already a reality at CHAdeMO. You can go to the website there. And this is already available. And by 2025, V2G could provide additional revenues and cost savings of $2 billion to global energy suppliers and offer consumer 50% saving on the household energy bill. And here are the systems available. And if you look at V2X certified products and home to vehicle to buildings, vehicle to load, vehicle to home, and vehicle to vehicle, etc. It's already available in the market. And also we are working with Vitality, who have signed an agreement with Honda and to develop V2G systems, wireless V2G systems. So we are part of that too. We are collaborating with Vitality and all this work. And I would like to thank our group, and without their help, I would not be able to present this work. And with that, and I will conclude my seminar. And thank you very much. I'm very happy to answer any questions if there are any.
If any question, kindly write to sir in chat box.
Yeah.
Sir, we don't have any much time because next session will be starting at 10 a.m.
Oh,
So
yeah.
I will
Sorry,
say,
I
sir,
took a little
what
long
thing
time.
I will share your email ID to participant and they will write it to you, sir.
Oh, no problem. Okay. Thank you very much.
Sarvan sir, please give for of things.
Okay. So is it all right? Did you hear
Yes,
very well? Any problems with that? No, it's okay.
No. Sarvan sir.
Yes, sir. Yes. On behalf of 5th ICCCA Organizing Committee, it's my immense pleasure to thank our keynote speaker, Professor Udaya Madawala, fellow IEEE, Department of Electrical and Computer Engineering, the University of Auckland, for this acceptance of invitation. It was a great opportunity for the students and researchers to listen to the advancements in V2X technologies. Your address on various challenges on power converter, battery, and integration will help them to work more on the same. In addition, the researchers will get a clean information to work for which control variables. It was an opportunity for the participants to update ourselves on the latest development in V2X technology. Thank you so much, sir, for your valuable time and support towards the conference. Thank you,
Thank
sir.
you. Thank you for giving me the opportunity. Okay, then bye.
Bye, sir.